In the previous chapter, we explored the concept of waves and defined a wave as being the propagation of energy through vibrations of media, such as waves in water or a pulse in a string. In this chapter, we will look at two specific types of waves, namely sound waves and light waves. Sound and light are two of the main ways that we explore and interact with the world around us. We use sound to hear and to communicate, and we use light to see the world. A sound wave is another example of a mechanical wave which requires some physical medium to propagate. We mostly associate with sound as waves through the air, thus the air itself is a vibrating medium that propagates the wave. But sound can also travel in water as well as in solids. Sound cannot travel in space though, where there is a vacuum and there is no medium to transmit the sound wave. An easy way to visualize the mechanical nature of sound waves is shown in this animation. The animation consists of an air column or tube that is opened at the right end. At the left end, there is a piston that can move back and forth. Each time the piston pushes forward, it pushes the air particles immediately in front of it, and this region of air becomes compressed. As the particle is pushed forward, it collides against the next particle, pushing that particle forward while it recoils back. This can be seen by observing some of the red particles in the animation. This process moves the compression region forward, thus propagating the sound wave. If the piston moves back and forth in simple harmonic motion, then a longitudinal wave is created inside the air column that is sinusoidal. As the particles that carry the sound energy move in simple harmonic motion, observe the motion of one of the red dots and you'll see. The displacement of the particles can thus be described using the wave equation previously derived in the Oscillations and Waves chapter, where the particle displacement is equal to its amplitude of oscillation multiplied by the cosine of kx plus or minus omega t, where k is the wave number and omega is the angular frequency. The plus or minus sign in the brackets represent the direction of the traveling wave relative to the x-axis. A negative sign means moving in the positive x direction, while a positive sign means moving in the negative x direction. An oscillating source creates periodic regions of compressions and refractions in the air column. Compressions are regions where there is a high density of particles, and refractions are regions where there is a low density of particles relative to the average density of the air in the column. The distance between successive compressions or successive refractions is equal to one wavelength of the wave. Because of the increased density, there is also a corresponding increase in the air pressure. Hence, sound waves can also be called pressure waves. Specifically, sound waves are pressure waves that occur within the audible hearing range of frequencies that allows us to hear the wave. The audible range for humans is around 20 Hz to 20 kHz. But this range varies between individuals. It can be shown, but not here, that the change in pressure can be given by BAK times the cosine of Kx plus or minus omega t, where B is the bulk modulus of the medium which the sound is propagating in. A is the displacement amplitude of the medium, and K is the angular frequency. The bulk modulus determines how much a material will compress under a given amount of external pressure. Recall back to the wave speed video in the previous chapter on wave speed, and you remember that the bulk modulus affects the speed which the sound wave travels through that material. Pressure is defined as a force applied over an area, so the unit for pressure is newtons per square meter. The product of the bulk modulus, the displacement amplitude, and the wave number in the bracket represents the amplitude of the pressure wave. What is the magnitude of the maximum change in pressure of a sound wave? The magnitude of the maximum change in pressure will occur when the cosine of the pressure equation is equal to plus or minus 1, being the biggest possible values for a cosine. So the maximum change in pressure is the amplitude of the pressure wave, which is the product of the bulk modulus with the displacement amplitude and the wave number. What then is the magnitude of the minimum change in pressure of the sound wave? The minimum change in pressure will occur when the cosine of the equation is equal to 0. So the minimum change in pressure will be zero. That is, the minimum pressure will be the pressure of the air in equilibrium when there is no wave. Comparing the equation for the displacement with the equation for the change in pressure, we see that pressure also varies sinusoidally, as can be seen in the animation, but it is out of phase with the displacement by 90 degrees, or 1/4 of a cycle. This means that wherever there is a displacement node, there is a pressure antinode. In other words, the particles that don't move as a result of the wave movement experiences the greatest pressure. In summary, sound waves are longitudinal mechanical waves caused by the vibration of particles in a medium. The particles vibrate in a direction that is parallel to the direction of the wave. All of the other properties of waves previously discussed, such as velocity, frequency, and wavelength, apply to sound waves as well. A sound wave can be described as a displacement wave or as a pressure wave.